This is Unit 2, Introducing Proportional Relationships. This is Lesson 7, Comparing Relationships with Tables. So we're going to focus on constructing tables throughout this lesson. And the first activity, adjusting a recipe. So they give you a recipe. The basic recipe is 5 lemons, 2 cups of water, and 2 tablespoons of honey. Now I constructed the table. They don't actually go in that direction in the notes for the teacher, but the whole idea of this lesson is to construct tables. So I would suggest constructing a table. You have 4 recipes, and it asks you in the first recipe to increase the amount of lemonade you have, but keep the taste the same. So you're running out of lemonade, you need more lemonade, you want to increase the amount that you make, but you want the taste to be the same. That's scaling up. We did that a while ago, so I can scale up this recipe by increasing the amount of lemons, increasing the amount of water, and increasing the amount of honey, all in the same way, using the same factor to do that. So 5 times 2 is 10, 2 times 2 is 4, 2 times 2 is 4. Or I could use the constant of proportionality. So that means, and this recipe number 2, you're going to make a lesser amount of lemonade but keep the flavor the same. So you would have to use 2 different scale factors for these rows. This row, from going from the basic recipe to number 1, use a scale factor of 2. To go from the basic recipe to recipe number 2, you use a scale factor of 1/2. You cut everything in half. So 5 times 1/2 is 2.5. 2 times 1/2 is 1. 2 times 1/2 is 1. Or you could choose to use the constant of proportionality, which is going to be the same factor. And that constant of proportionality you get from, remember, you're going to call the amount of water y and the number of lemons x. So 2/5 is the constant of proportionality. So what that means is the amount of water that you're going to use is 2/5 the number of lemons. So 2/5 times 5 is 2. 2/5 times 10, so the amount of water you're using is 2/5 the amount of water. So 2/5 times 10 is 10 divided by 5 is 2. 2 times that 2 right there is 4. So you're going to use 4 cups of water. And we're not going to deal with the honey in these calculations, but it would be the same. The constant of proportionality would be the same in this case because the amount of the units of water is the same as the number of units of honey. All right, so if you're going to make a lesser amount, you can use the same constant of proportionality, 2/5, but begin with just fewer lemons. So 2.5 lemons, which is 5.5. The constant of proportionality, I'm sorry, not 5.5, but 5/2. The constant of proportionality is 2/5. You multiply those together. Notice that those are multiplicative inverses, also called reciprocals. Whenever you multiply reciprocals together or multiplicative inverses together, it always equals 1. That's the definition of a multiplicative inverse. You multiply both of them together, they always equal 1. Now in recipe number 3, they want you to make a recipe that has a stronger lemon taste. So that means you're going to use more lemons compared to the amount of water, or cut down the amount of water compared to the number of lemons. That is the same thing. So I'm going to compare this recipe with recipe number 1. So I'm going to start out in both cases with 10 lemons, but for the amount of water, I'm going to use half the amount of water for recipe number 3. So 4 times 1/2 is 2. So I'm using less water for the same number of lemons. So this is going to have a stronger lemon flavor. Now if I figure out the constant of proportionality, that is 2/10. And 2/10 is the same as 1/5. So notice what's happened to the constant of proportionality. That's been cut in half. Instead of 2/5, it's 1/5. So now I'm using 1/5 the number, the amount of water I'm using is 1/5 the number of lemons. So you start out with 10 lemons. 1/5 of 10 is 2 cups of water. So how much water do I need? Well, you need 1/5 the number of lemons that you have. I have 10 lemons, So I need 2 cups of water. In this case, when the recipe is the basic recipe, you have 10 lemons, then I need 2/5 that number of lemons for the cups. The number of cups of water are 2/5 the number of lemons, or 4 cups of water. And finally, number 4 says, how do you make this recipe have a weaker lemon taste? Well, you're going to have to increase the amount of water that you use compared to the number of lemons. And for this one, actually, this is going back to the equation. So remember that this tells you that the amount of water is 2/5 the number of lemons. Use 5 lemons, you're going to use 2 cups of water. This one tells you that the amount of water is 1/5 the number of lemons. So you use 10 lemons, you're going to use 2 cups of water. And if you want a weaker lemon flavor, you're going to have to use more water for the number of lemons. So this constant of proportionality is 4/5. It's also twice as much water with the same number of lemons. So 2 times 2 is 4 cups of water for the same number of lemons if you compare this to the basic recipe. But this constant of proportionality is 4/5. So that tells you that you're going to use 4/5. The amount of water you're going to use is 4/5 the number of lemons. That's what that says. The amount of water is equal to 4/5 the number of lemons, because the amount of water divided by the number of lemons is 4/5. So the amount of water that you need is 4/5 the number of lemons. So this is going to have a weaker lemon flavor because you're using much more water. Now, if you look at these in order, this is the strongest lemon flavor. So the amount of water is 1/5 the number of lemons. So not very much water. You got 5 lemons, 10 lemons. You're going to use 1/5 the number of lemons for the amount of water that you use. This one has a weaker lemon flavor. This is the basic recipe. This one says you're going to use 2/5 the number of lemons for the amount of water. So I have 5 lemons. I'm going to use 2/5 of 5, or 2 cups of water. And this last one has the weakest lemon flavor. So this is 4/5. So I'm going to use 4/5 the number of lemons for the amount of water. So how many cups of water I need? You need 4/5 the number of lemons. And so notice that this is 4 times weaker, or this one is 4 times stronger than recipe number 4. And recipe number 4 is 2 times weaker, or the basic recipe is 2 times stronger when you compare number 4 to the basic recipe. This is lesson 7, comparing relationships with tables. This is activity 2, visiting the state park. And in this activity, you're given a table, you're given some information about groups of people entering a state park, and you're given a table to keep track of that information and eventually figure out the total entrance cost in dollars. And so here's that same table, and here are the questions. And the beginning information is that there's the cost per person. So each person has to pay $2 for their entrance fee, plus an additional $6 as a group for the vehicle that's entering the park. And so that really calls for added columns to this table. Now, this whole lesson is about using tables to solve problems. And so I would suggest adding a few more columns to keep track of the information in the situation. So one of the columns is the cost for just the number of people entering the park. So forget about the vehicle for a moment, and just how much does it cost for just the people in the car? So the ranger, you drive up to the entrance, the ranger looks in the car and says, okay, it's going to cost, let's see, you have 5 people, $2 per person. That'll be $10 for the number of people in the car. And then in addition, you have to add the cost of the vehicle. So that's another $6. And then so if you're going to split the cost evenly amongst everybody in the vehicle, what's the cost going to be for each person, the total cost for each person? So for example, 2 people are entering the park. The ranger looks in, sees 2 people. That's 2 times 2. That's $4. Plus you have to add another $6 for the vehicle. So that's a total cost of $10. So what's the cost per person going to be? So you're going to look at your friend. You're going to the park with a friend. You look over, and you need to get from that person $5, because each of you are going to pay $5 to enter the park. And let's say that there are 4 people in the car. Well, you look into the car, the ranger looks in the car and sees 4 people. That's 2 times 4 is $8 for all the people in the car, plus another $6 for the vehicle. Let's say that there's a van that's going to the park. It has 10 people in the van. Look in, count 10 people. That's 2 times 10 is $20, plus another $6 for the van. So that's a total of $26. Or the last question down here, question number 3, is what if it's a bus of 50 people? Well, you look in, you see 50 people. How many people you have in the bus, sir? You have 50 people. 2 times 50 is $100. And plus it's going to cost you another $6 for the bus. So if you take that total entrance cost and divide it by the 2 people, that's $5 per person. Now look what's happening. Each person pays $2. Plus, you take the $6 and you divide that between the 2 people. And that's $3 per person, so 2 plus 3 is $5. $10 total divided by 2 is $5. In this case, with 4 people in the vehicle, that $6 is going to be divided among the 4 people. So that's going to be $2 per person plus another $1.50. $6 divided by 4 people is $1.50. So each person pays $2 for themselves plus $1.50 for the vehicle. So that's the total of $14 divided by 4. Well, if it's 10 people, that $6 now is going to be split up among those 10 people. So each person is going to have to pay 60 cents in addition to the $2 for them to get into the park. So it's going to be $2.60. It's $26 divided by 10 people. Or let's say that there are 50 people. That $6 is going to be divided among those 50 people. Well, 6 divided by 50 is the same as 12 hundredths. 12 hundredths is the same as 12 cents. So each person has to pay 12 cents plus the $2 that it costs for them to enter the park. So it's $2.12. Now this is not a proportional relationship. It's not increasing. If you double the number of people from 2 people to 4 people, the price per person doesn't double from 5. The price per person doesn't stay the same. Or if you double the number of people, the total price doesn't double from $10 to $20. But the cost for just the number of people, forget about the cost of the vehicle, the cost for just the number of people is a proportional relationship. So you double the number of people from 2 people to 4 people. The cost for those 2 people is $4. That does double to $8. Or if it's 5 times the number of people from 2 people to 10 people, then the cost for just the people goes from $4 to $20. 5 times 4 is $20, or 25 times 4 is $50 for 50 people. So 25 times 2, 25 times more number of people, that's 50. The cost for just those people is going to increase by 25 times. So that is a proportional increase just for the cost for the people. But then you add the $6 in every case, that makes that increase not proportional. So there's no constant of proportionality. There's no constant cost per person. That cost changes because you have to spread that number, that $6 among a different number of people. So that amount's going to change. The more people you have going to the park together, the less they have to pay for the vehicle. So it is not a proportional increase. This is lesson 7, comparing relationships with tables, and this is activity 3, running laps. And in this activity, we're going to compare the running times of 2 people, Han and Claire. It's run around a track. Their coach keeps track of their time. and we're going to look to see if one or both of them are running at a constant speed or a constant rate throughout their run. If they are, then that is a proportional relationship. So the first one is Hans' run. And I wrote up here a question mark under the constant of proportionality, or over the constant of proportionality, because we don't know if there is a constant of proportionality yet. The way we're going to figure that out is to take the number of minutes and divide that by the number of laps. That's going to give us the minutes per lap of Hans' run. And so that's y divided by x. And if it is a constant rate, then that will be a constant of proportionality. So in the first time is after 2 laps, 4 minutes per 2 laps, that's 2 minutes per lap. So y divided by x gives you an answer of 2 minutes per lap. After he runs 4 laps, that's taken him 9 minutes. So that's 9 minutes per 4 laps, and works out to be 2 1/4 minutes per lap. After 6 laps, it takes him 15 minutes to run 6 laps. That's 15 divided by 6, or 2.5 minutes per lap. So these are not the same. So there's not a constant of proportionality. So 23 divided by 8 after 8 laps, 23 minutes. That works out to be 2 7/8 minutes per lap. So if you really want to see how these are changing, one thing to do is to change them all to eighths. And so this is 2 1/4 is 2 2/8, 2 1/2 is 2 4/8, and then 2 7/8 is 2 7/8. And as a little bit of practice for working with fractions and developing more your sense of numbers, you might just show arithmetically or using arithmetic how to do that. Well, if you have 4 halves, to change that to eighths, you have to multiply both the number of laps by 4 and the number of minutes by 4. So 2 times 4 is 8, 4 times 4 is 16, so that's 16 eighths, or 16 minutes per 8 laps. It's 2 minutes per lap. For 9 minutes for 4 laps, you have to multiply both by 2 to get to 8. 4 times 2 is 8. 9 times 2 is 18. So that's 18 eighths. And what you can do in this case is pull out 16 eighths. That's equal to 2. And you're left with 2 eighths. So this is now 2 2/8. So you've gone from 2 minutes per lap to 2 2/8 minutes per lap. Next one is 15/6. It's a little bit harder to see for this one. You can multiply the 6 by 1/3 to get to 2, and then 2 times 4 to get to 8. If you're going to do that, you have to do the same thing to 15. 15 times 1/3 is 5. 5 times 4 is 20. So 15/6 is the same as 20 eighths. And again, you can pull out the 16 eighths, which is 2, and you're left with 4 eighths. This is 2 4/8, 2 4/8. Now you might be able to see that you can do this in one step as 6 times 4/3. Because if you multiply by 1/3 and then you multiply by 4, that's the same as multiplying by 4/3. Well, 6 divided by 3 is 2. 2 times 4 is 8. If you do the same thing with the 15, 15 divided by 3 is 5. 5 times that 4 would be 20. So you get the same answer, 20 eighths, which is 2 4/8. Finally, the last one, 23 eighths. Pull out the 16 eighths, that's 2. You're left with 7 eighths. So this is 2 7/8. Hans' minutes per lap, or his pace, or his lap time, is getting longer. He's taking more time to run each lap. So he's slowing down. It's not a constant rate. That means it's not proportional. If you double the number of laps, the amount of time does not double. Actually, it's more than double because he's slowing down. So he's taking a longer time. On the other hand, for Claire, she's running at a constant rate. Every time you take her number of minutes and you divide it by the number of laps, you get 5 halves, 5 minutes per 2 laps. That works out to be 2.5 minutes per lap. So the constant of proportionality in this case is 5 halves. You can write it as 2.5. It's better to leave these numbers as fractions, 5 halves. We'll get into that later. So 10 minutes, 4 laps in 10 minutes. You can cancel, you can factor out the 2. You're left with 5 halves once again. 15/6, cancel out the 3's. You're left with 5 halves again. 20 eighths, cancel out the 4's. you're left with 5/2 again. So to summarize, Han is not running at a constant rate. There is no constant of proportionality. He is actually slowing down every 2 laps. He's taking more time to run the laps every 2 laps. So it goes from 2 to 2 2/8 to 2 4/8 to 2 7/8. Claire, on the other hand, is running at a constant rate. Her constant of proportionality is 2.5 minutes per lap. Now, she could be speeding up or slowing down in between and ending up running at what looks like to be a constant rate after the time is taken every 2 laps. One way to show somebody that it truly is a constant rate, it truly is a proportional relationship, is to express it as an equation. Once you do that, then that forces every amount of time to be related to the distance in a proportional way. So to do that, to write the equation, it's time divided by distance, which is 5 divided by 2. So what that says is that the units of time are 5/2 the units of distance. So the units of time are going to be more. Actually, they're going to be 5/2 more, 2.5 times whatever the unit distance is. So if the distance is one lap or 1 unit, the time is going to be 2.5 minutes or 5/2 minutes. So the equation is that the time is 5/2 the distance. So the time is equal to 5/2 the units of distance. All right. This is lesson 7, comparing relationships with tables. And this is activity 4, apples and pizza. In this first table, the question is the cost of apples proportional to the pounds of apples? And so the way to figure that out is you look for a constant of proportionality. Is there a constant cost of apples per pound for regardless of how many pounds of apples you purchase? And so you take the cost of the apples and you divide it by the number of pounds and see what you get. And in every case, you get $1.88 per pound of apples. $5.64 divided by 3, $7.52 divided by 4, $9.40 divided by 5. So in every case, regardless of how many pounds of apples you purchase, the cost per pound is always the same. So that means that there is a proportional relationship. That constant proportionality is equal to $1.88 per pound of apples. And so what that proportional relationship means is that regardless of the increase in pounds of apples, regardless of what you multiply the number of pounds of apples by, so 2 pounds of apples times 2 is going to give you 4 pounds of apples, the cost of the apples are going to increase with that same factor. So they are going to increase by a multiple of 2. If you were to multiply the 2 pounds of apples or the 1 pound of apples by 5, then the cost of the pounds of apples are going to increase by a factor of 5. So $1.88 times 5 is going to give you $9.40. That is what a proportional relationship means, that the units, the number of units in the column on the left, the x values, if you will, increase by a factor, and the number of units in the column on the right, the y values, increase by that same factor. So that is a proportional relationship. There is a constant of proportionality. And so the cost is 1 88/100 times more than the number of pounds. So notice that the cost is a bigger value. It's larger than the pounds of apples. It's 1 88/100 times larger. So the cost is 1 88/100 times the pounds, the number of pounds of apples. So cost equals 1 88/100 times the number of pounds. It is a proportional relationship. On the other hand, the number of toppings on a pizza and the cost of the pizza is not a proportional relationship. So if you take the cost of the pizza and you divide it by the number of toppings, you get a value that is not a constant. So I should have put a question mark here. It's not a constant of proportionality. So it begins with $11.99 divided by 2. That's $6 per topping divided by 3. That's $4.50 per topping. $14.99 divided by 4. That's $3.75 per topping. So notice that as the number of toppings increases, the cost of the pizza per topping decreases. So it's going down farther and farther and farther. So this is not a proportional relationship. There is not a constant of proportionality. Now what you can do is take this idea, and if you want to play around with this a little bit, look at it as in the way that you're going to look at this as an 8th grade. So there's a base price of the pizza. That is $8.99. And the cost of each topping is $1.50. So if I'm going to figure out the total cost of the pizza, I'm going to take the number of toppings, 5 for example, and I'm going to multiply it by this $1.50, and I'm going to add $8.99 to that. Well, how do you get this? How do you figure out that it's $8.99 is the base price of the pizza, and the cost of each topping is $1.50? Well, you look at the change between adding one topping compared to the cost of the pizza when you add one topping. So when you add one topping, it goes from $11.99 to $13.49. That's an increase of $1.50. Do that again, add one more topping, the price increases another $1.50. Do that again, add one more topping, the price increases $1.50. That means the price is increasing $1.50 for each topping. And how do you figure out the base price of $8.99? Well, that's 2 toppings. Well, if it increases $1.50 for each topping, just multiply 2 times $1.50. That gives you $3. Subtract that $3 from $11.99. That's the cost of 2 toppings. Do that subtraction. That gives you a base price of the base price of the pizza of $8.99. So try to play around with that a little bit. See if you can understand how you get this equation. This is adding $8.99. This part is proportional. The cost per topping, if you look at just that part of the pizza, not the total cost, that cost is proportional. It's $1.50 per topping. But then you have to add on to that the base price of the pizza, $8.99. This is the summary for Lesson 7, comparing relationships with tables. And here are a couple of tables based on the cost of smoothies from 2 different smoothie shops, Shop A and Shop B. And in Shop A, if you look down the cost per ounce, or the number of dollars per ounce, you see it's the same. Regardless of the size of the smoothies, the price is always the same per ounce. So you get that answer by dividing the price by the size of the smoothie. That's the constant of proportionality. So take the price, which is the Y column, divide that by the size, which is the X column, and you always get 75 cents per ounce, or 75 hundredths of a dollar per ounce. Now notice that the price of the smoothie is always less than the number of units of dollars is always less than the number of units of ounces for the smoothie. It's always 3/4 of the ounces of the smoothie. So a person that is serving you, they're going to figure this out, how much you owe, by taking the size of the smoothie and multiplying it by 75 hundredths to get the price, because the price is 3/4 of the size of the smoothie. On the other hand, when you go to Smoothie Shop B, there is no constant proportionality. The cost per ounce actually decreases as the size increases. So this is as if in this shop they're giving you a break on the amount they're charging you per ounce if you buy more. So if you buy a larger size, you have to pay less per ounce of smoothie. That's why this price is going down. And so here's an equation for the shop that has a constant proportionality. you can write an equation for that using that constant of proportionality in that equation. So the price is equal to 75 hundredths the size of the smoothie. And I like writing this to make sure that I'm looking at that relationship correctly. So I look at the price per size, and that equals 75 hundredths. So that tells me that that price is 75 hundredths or 3/4 the number of units of the smoothie, the number of ounces of the smoothie. So for 1 ounce, it's 75 hundredths times 1 ounce is the price. 75 hundredths times 2 ounces is the price. 75 hundredths times 3 ounces is the price. Because that's what this means. When you take the price and you divide it by the size, that answer is always 75 hundredths. It tells you that you need 75 hundredths times that size to get the price. So the price is 75 hundredths of the size. So the price is 75 hundredths of the size, or the number of ounces of the smoothie. And so they say that the relationship could still not be proportional if there's a different size on the menu that did not have the same price per ounce. So let's say that if you buy a giant size, they decide, okay, we're going to give you a big break on that. We're only going to charge you 50 cents per ounce. So that would make the relationship no longer proportional. Or let's say that if you buy just a single ounce, you have to pay $1 for that. So they have a minimum price because they still have to cover the cost of the container if they're selling you smoothies. And for smoothie shop B, there is no constant of proportionality, so it is not a proportional relationship. And so what they say down here is that the two values, the two quantities are proportional, will always have the same quotient. So when you divide, you always get the same answer, the same quotient, and that is a proportional relationship. And I'd like to look at that a little bit differently, that if you increase let's say the X column, the size of the smoothie, if you double that size, then you're going to double whatever the values are in the Y column if it's a proportional relationship. So now you're going to double the price. So if you go from 8 ounces to 16 ounces, the price is going to double from $6 to $12. So that is a proportional relationship. You have pairs of numbers. If one pair increases by a factor, the second pair is going to increase by that same factor. This is scaling. This goes back to what we did a long time ago. This is scaling, and you can figure out what the price is by using the constant of proportionality. That's constant every time, but if you scale it up, you're increasing by the same factor. That is a proportional relationship. Now, if you write an equation, then that tells you that every single size, the price of every single size is proportional to that size. So that takes away the possibility of having a large size for a smaller amount per ounce. So once you write this equation and you use that equation, you're going to figure out the price based on 3/4 the size, whatever that size is, whether it is 1 ounce or 24 ounces, whatever it is, it's always going to be 3/4. The price is always going to be 3/4 of that size, or 75 hundredths of that size. These are the practice problems for Lesson 7, comparing relationships with tables. And the main idea of this lesson has been to construct tables that contain the relationships within them and figure out whether or not those relationships are proportional. And the way to do that is to figure out whether or not there is a constant of proportionality. And sure enough, 4 of these 5 practice problems have to do with constructing tables or looking at information within tables and figuring out whether or not the relationships are proportional. This is problem number 1. And it just simply says, here are 2 tables containing relationships, and figure out whether or not those relationships are proportional. The table on the left is looking at the distance that a listener is away from a sound, and sound is measured in decibels. And so the distance that the listener is away, 5 feet away, and the person hears that sound in this measure called decibels, so they hear it at a level of 85 decibels. 10 feet away, they hear the same sound at a level of 79 decibels. 20 feet away, 73 decibels. 40 feet away, 67 decibels. And so to figure out whether or not that relationship is proportional, so if you double the distance, does the sound increase by 2 times? If you triple the distance, the sound increase by 3 times. Well, first of all, this distance decreases. As you go farther and farther away, the distance gets less and less. But it also gets less by a relationship that is other than, in this case, it would be halving, cutting it in half, or cutting it by 1/3, or cutting it by 1/4. And so it's not a proportional relationship. And the way you confirm that is to figure out if there's a constant proportionality. So you take the column that's usually labeled y, and so it's the column on the right, and you divide the values in that column by the values on the left, which are usually labeled x. So this is sound, the sound level, divided by the distance. And so the sound level divided by the distance, you see these values, 17, 7 9/10, 3 65/100. They're not the same. So there is not a constant of proportionality, meaning you cannot take the value on the left, the distance, and multiply it by a constant to figure out what the volume is. You just can't make that calculation because it's not a proportional relationship. Likewise, the table on the right is the cost of drinks. A fountain drink is a drink that you get at a counter in a restaurant or a pharmacy, and let's see, the number of ounces of that drink and compared to the cost. And so as the number of ounces increase, so if you double the ounces or triple the number of ounces, the cost double or triple. Well, in this case, you can't look at values that are doubled or tripled because the table is not giving it to you. So you figure out a constant of proportionality. You take the cost and you divide it by the volume, and you see if you get a constant value. If you do, that means then you could take the volume, multiply it by that constant, and figure out how much it's going to cost you. But because it's not a proportional relationship, you cannot make that calculation. So this is not a proportional relationship, and this is not a proportional relationship. So that's problem number 1. This is problem number 2, and this is similar to the first problem in that here's a table, and you're supposed to figure out whether or not this relationship of distance traveled in a taxi is proportional to the cost of taking the taxi, the price in dollars. And so in this situation, the first 1/10 of a mile that you travel in the taxi costs you $1. So whatever you do, however far you travel, that first 1/10 of a mile is going to be $1. And every 1/10 of a mile after that will cost you 10 cents. So here is the distance that you traveled. And what you have to do in this case, or what I did anyway in this case, is I separated out that 1/10 first. So 9/10 is 1/10 plus 8/10. 20/10, which is 2, is 1/10 plus 19/10. 31/10 is 1/10 plus 30/10. And 100/10 is 1/10 plus 99/10. So I separated out that 1/10 first because that costs you $1. And so here's that $1 in each case that you add on. And the first part of this calculation is the number of tenths times 10 cents. So 8 times 1/10 of $1, 19 times 1/10, 30 times 1/10, and 99 times 1/10. You calculate that and you get the value for y. And to figure out whether or not there's a constant of proportionality, you take the y calculation and divide that by the x value. So this is $1.80 divided by 9/10. And that's right here. Here's y divided by x. This is to figure out if there's a constant of proportionality. So $1.80 divided by 9/10. $2.90 divided by 2. Here's the $2.90 divided by 2. $4 divided by 31 tenths. And $10.90 divided by 10. And you can see that it's not constant. It's not constant because you're adding in this problem. You add $1 each time. That makes the relationship not proportional, and there is not a constant of proportionality. Now, the number of tenths that you travel after that first tenth, that is proportional to the price. It's 10 cents for each 1/10 of a mile. So the number of tenths that you travel afterwards, 8 tenths, times 1/10. 19 tenths times 1/10 of a dollar. 30 tenths times 1/10 of a dollar. So that part is proportional, and that's actually how I figured it out. I calculated the number of tenths, which is x, and multiplied that by 1/10, which is 10 cents. So how many 1/10 of a dollars are there? And then you add that $1 afterwards. So here's the equation once again. And this first part is proportional, but it's then adding that $1 that makes it not proportional. So it's not a proportional relationship because there is no constant of proportionality. I wanted to add a bit more to problem number 2 because I realized I was using a constant of proportionality of 10 cents or 1/10 of a dollar. But if you take the y value here, the price based on the number of tenths after that first dollar, so this would be 80 cents, and this would be $1.90, and this would be $3, and you divide that by the number of tenths after that first tenth. So 80 cents divided by 8 tenths, $1.90 divided by 19 tenths, $3 divided by 30 tenths. Those are all equal to 1. So that constant of proportionality is 1, but I'm using a constant of proportionality over here of 1/10. So I was wondering, why is that? Why am I using a constant of proportionality that's different than what I get when I do the calculation over here? So I made 2 copies of that same table, and I changed the x values just slightly in each one. Over here, this is the value that you get in the previous page. So the number of tenths after that first tenth. So this is 8, not the number of tenths, it's the mileage after that first tenth. And that's the difference right there. So this is 8 tenths, this is 19 tenths, this is 30 tenths, and 99 tenths. The right side is the same in both tables. So you pay 80 cents, $1.90, $3, and $9.90. So you make that calculation for the constant of proportionality, y divided by x, and you see that it comes out to be a value of 1. So this equation then is, well, let me just mention, so this is 80 cents divided by 8 tenths, that's 1. This is $1.90 divided by 1 and 9 tenths, that's 1. This is $3 divided by 3, that's 1. This is $9.90 divided by 9 and 9 tenths, that is 1. So this constant of proportionality is 1. So y is equal to 1, the constant of proportionality, times x. So that means that y is equal to x. And if you look at it, that's true. So the price is the same as the number of tenths after that first tenth. So it's 8 tenths, 80 cents, 19 tenths, $1.90. But over here, this is the one that I was using in the calculation. Here I'm counting the number of tenths after that first tenth. So I'm not writing down the number of miles. So it's 8 tenths of a mile, but it's the number of tenths is 8 tenths. This is 19 tenths for 19 tenths miles. This is 30 tenths for 30 tenths miles. And this is 99 tenths for 99 tenths miles. So this is the number of tenths. And this is what the text says. The text says it's 10 cents for each additional 1/10 of a mile. So I counted 1/10 miles. And over here, this is the price that you pay. So now you make that calculation of the constant of proportionality. So this is this y divided by this x. And in every case, that turns out to be 1/10 or 10 cents. So 80 hundredths divided by 8 is 10 hundredths or 1/10 or 10 cents. $1.90 divided by 19 is 10 cents. That's 1 90 or 19 tenths divided by 19 is 1/10. This is 30 tenths or $3 divided by 30 is 1/10. And this is 99 tenths divided by 99, so that's 1/10. So this constant of proportionality turns out to be 1/10. You write that in the equation that y is equal to 1/10 x. So now notice that the constant of proportionality, so why are these both the same? The constant of proportionality is 1/10 on the right table. It's 1/10 of what's on the left, but the value that you're multiplying, the x value, this is 1/10 of the values on the table on the right. So the constant of proportionality is 1/10 as much, but what you're multiplying it by is 10 times as much. So 1/10 times 10 is 1, so you end up with the same answer, the same calculation. I don't know if it's the same calculation, but you end up with the same answer. So interesting how the wording can change how you write the calculations and how you end up with the constant of proportionality. So this was 1/10 of a dollar or 10 cents for each additional 1/10 mile. This is problem number 3, which is the story of the race between the rabbit and the turtle, oftentimes described as the race between the tortoise and the hare. And you guys know that in this story, the tortoise or the turtle moves at a very slow and steady pace. It doesn't speed up, it doesn't slow down. No matter what's happening, it moves at that same pace. Well, that's a constant rate. And there's going to be a constant of proportionality, and it's going to be proportional. The turtle's time is going to be proportional to the turtle's distance that the turtle runs. And I hesitate to say run. I don't know if a turtle actually runs or not. But the rabbit, you guys may remember that the rabbit slows up, slows down, speeds up, actually at times even takes a rest, stops. So that is not a constant rate. So there is no constant of proportionality for the rabbit's run. Even though the rabbit runs much faster, you know from the story that the rabbit eventually gets very tired and slows down. So we're going to take a look at those things within these numbers. And when I looked at this, I just blindly started doing the calculations. So I made the time the y value, because usually the column on the right is labeled y and the column on the left is labeled x. And the constant of proportionality is y divided by x. In other words, what value times 108 equals 2? And so you do that calculation, 2 divided by 108, 7.5 divided by 405, 10 divided by 540, 32 and 75 hundredths divided by 1,768 and 5/10. You do those calculations, you get the same value each time, and it's a messy number. It is 185 10,000ths. What that means is 185 10,000ths of a minute per meter. So that rabbit runs the turtle moves 1 meter. Now take your hands and hold them out about twice your shoulder length. That's about a meter. And imagine the turtle moving that distance in this amount of time. 185 10,000ths of a minute. Well, that's pretty hard to think about. So we're going to redo this in a moment, but you go through the same calculations for the rabbit. So 1 divided by 800. This is a much smaller number because it's taking much less time on average to run these 800 meters. So what's the time? What's the number of minutes per meter? It's a very small number, much smaller than this number over here because it's taking much less time. But notice this number gets larger over time. So what's the rabbit doing? The rabbit is slowing down. The rabbit's taking more time to run a meter. So its time is increasing in terms of minutes per meter. This number is getting bigger. And if you compare the two, now the turtle is moving at a constant rate. So any of these distances, you can use this rate, for the turtle's movement. So right here, they choose different meters over here, so it's a little bit hard to compare, but you can use this distance, for example. And so the rabbit's time for this distance is, now this is 100 thousandths. So this is 1,806 hundred thousandths. And the turtle's time for this same distance, because it's moving at a constant rate, is going to be 1,852 hundred thousandths. So I'm just going to say 1852 and 1806. Now this time is smaller. So for this distance, the rabbit is taking less time. It's actually, the difference is 46 hundred thousandths faster of a minute faster for this time. But then you go to the next time, this time right here, 1,524 meters, and now the rabbit has slowed down even more. And the rabbit has slowed down to a slower rate for these 1,524 meters than the turtle. The turtle has moved at 1852 minutes. This is 100 thousandths of a minute per meter. The rabbit is 2132. You figure out that distance, and the turtle actually moves 280 100 thousandths of a minute faster for this time than the turtle. So the turtle is moving, than the rabbit. So the rabbit's moving slower, the turtle's faster over here. The rabbit's faster, the turtle's slower. So at this point, from this distance to this distance, the rabbit gets so tired that it moves at a much slower rate than the turtle, and its overall rate to get to this point takes more time than what the turtle takes. Hard numbers to look at, deal with. So let's switch it. Let's look at, instead of time per distance, maybe it's easier to look at distance per time. And that's just going to be switching and looking at the distance per time. So it's x divided by y. So now this is going to be the constant of proportionality. So it's how much distance per minute do each of these characters run. And for the turtle runs or moves at 54 meters per minute. So 108 divided by 2 is 54 meters per minute. That, by the way, is the reciprocal of this one, of the minutes per meters. This simplifies to 1 over 54. So 1 minute per 54 meters, or 54 meters per 1 minute. And so you do that calculation now, and you see that it's always 54 meters per 1 minute. And so you get down to here, and you see that the x value is always 54 times the y value. So whatever x is, that's going to be 54 times y. So 54 times 2 is 108. So x is 54 times y. So that's the equation. So the number of meters is equal to 54 times the number of minutes. Now notice that the units for meters is much larger than the units for time, and actually the units for meters for this problem is going to be 54 times the units for minutes. So 1 minute is going to equal 54 meters. 2 minutes is going to equal 108 meters. Over here for the rabbit's time, the rabbit starts out really fast, 800 meters in 1 minute. Now think about that. That's more than 10 times as fast as the turtle starts out. The turtle starts out 10 times 54 is 540. So this is even faster than 10 times. I could do that calculation exactly, but let's just leave it as more than 10 times faster. But then after 5 minutes, the rabbit has slowed down to about 3 times faster. This is 180 meters per minute. So in 1 minute, at this speed, the rabbit's moving 180 meters in 1 minute. And this speed is even slower. So this is almost the same rate as the turtle to get to this point. And this is what we saw before. So now the rabbit has slowed down to a little bit more than 55 meters per minute. And finally, the last one, the rabbit's even slower than the turtle now at 46, let's say 47 meters per minute. So the rabbit keeps slowing down, slowing down, slowing down, slowing down. Imagine it's getting more and more tired, so it can barely even move. And so the turtle just keeps moving at this slow pace and eventually passes the rabbit and wins the race. So this is meters per minute, and the previous one we figured out minutes per meter. Now, it's even easier to look at this problem instead of looking at minutes, meters per 1 minute. What is this per second? How fast is and let's just look at the turtle now. How fast is the turtle moving each second? And so to figure that out, change this 1 minute to 60 seconds. So 60 seconds. Now notice that seconds are a lot smaller unit than minutes, so you're going to need a lot more seconds for that same amount of time. Actually, you're going to need 60 times the number of seconds. So 60 seconds divided by 54 meters is going to give you the number of seconds per 1 meter. So imagine you take that 60 and divide it up into 54 equal small parts. Each one of those parts is going to be a little bit more than a second. So 60 seconds for 54 meters is about 1 1/10 or 1 1100 seconds per meter. So a little bit more than 1 second for each meter. And you can also calculate it this way. Take the value we got before. This is the 1,852 100,000ths times 60 seconds per minute times 60. That's going to give you the amount of time per second. You're going to get the same answer, 1 1100 seconds for each meter. Now, it's better. It's easier to look at. It's easier to think about. So imagine 1 meter and then count to a little bit more than a second. And imagine that turtle moving through that distance, 1 meter, in a little bit more than 1 second. And this is going to be even easier to visualize if you look at it. How far is that turtle running or moving per second? Well, that's just the reciprocal. It's 108 meters per 2 minutes, which is 54 meters per minute, and then just change the minute to 60 seconds. 54 meters per 60 seconds. So now you're going to take that 54 and divide it up into 60 equal parts. And so each part's going to be a little bit less than 1. As a matter of fact, it's going to be 9/10. 6 times 9 is 54. 6 times 10 is 60. Cancel out the 6's, or factor out the 6 is a better way to say it. It's 9/10 of a meter per second. So now count 1 second, 1001, and imagine that turtle running at a length that's about twice your shoulder width. That's about a meter. So 1001, and personally, I think it's too fast. I don't think that a turtle can move that fast. Imagine setting down a turtle, saying go, and how far is it going to move in 1 second? It's not going to move close to a meter in 1 second. It's going to be much slower. So just a discussion to have about the problem. What would be a reasonable pace or a reasonable speed for the turtle? Now remember, these two values, this is minutes per meter, and we change that to seconds per meter, and this one is meters per second. So this is seconds per meter, this is meters per second, and they are reciprocals of each other. And what that means is they are multiplicative inverses. So if you multiply these two numbers together, you're going to get an answer of 1. That's the definition of a multiplicative inverse. Multiply them together, it equals 1. So 1 and 1100ths times 9/10. You get 0.999999. It's going to continue on forever. And it's actually equal, if you didn't use decimal values here, it would equal 1.0. So this number right here is actually 10/9. And this is 9/10. Multiply them together, you're going to get 1. All right, so lots to think about in this, on the surface, relatively easy problem to do. But think about changing it to easier units to think about. And it really, is the answer reasonable? And I don't think the answer in this case is reasonable. Turtle's moving too fast. This is problem number 4, and you are given 4 tables in which you are to find the constant of proportionality for each. And so to figure out that constant of proportionality, I usually take the right column and divide it by the left column, because if you do that, then you're answering the question, what do you have to multiply, in this case, A by to get to B? Well, that answer is B divided by A. And so in this case, the constant of proportionality is 14 divided by 2 is 7, 35 divided by 5, 7, 7, and 7/3 divided by 1/3 is also 7. So each one of these, if you take 2 times 7 is 14, 9 times 7 is 63. So that constant of proportionality tells you what you have to multiply by to get to B. So B is equal to 7 times A. I didn't put the 7 here, but I did write here. And so if you write this down here, if you look at this, it's 7/3 is 7 times 1/3. So it tells you that the B value is 7 times the A value, because 7/3 divided by 1/3 is equal to 7. So 7/3 is 7 times 1/3. Well, that makes sense. 7 times 1/3 is, in fact, 7/3. So B is equal to KA is the form of that equation, same as Y equals KX. So over here, it's more of the same. 360 divided by 3, 600 divided by 5, 960 divided by 8, 1,440 divided by 12. All of those are equal to 120. Now, if you divide each of these by 10 and just work with 36, 60, 96, 144, you might be able to see that that's 12 in each case. 36 divided by 3, 60 divided by 5, 96 divided by 8, and 144 divided by 12. So 1,440, actually, let me go back to this just for a second. So if you divide that by 10 and use 144, then you have to, and figure out that's 12, then you have to multiply that 12 by 10 to get the 120. So 1,440 is 120 times 12. So the equation is B, 1,440 equals K, 120 times 12, which is A. So that's, again, in the form Y equals KX. Next one, a little bit harder, because now you're making the B value, which is the answer, B is equal to K times A. This is smaller, so you have to multiply each of the A values by a fraction to make them smaller. Well, what is that fraction? It is 1/25. So 3 divided by 75, 8 divided by 200, 61 divided by 1,525, and 4/10 divided by 10. Each of those, if you simplify them, they are all equal to 1/25, or 1/25. I played around with this a little bit. If you divide each of these by 25, that's the same as multiplying by 1/25. So 75 divided by 25 is 3. So it's 3 times 25. I guess I didn't write that right here, but it's 3 times 25, and the 3's factor out and gives you 1/25. But I did here. So 200 divided by 25 is 8. So 8 times 25, and that's 8/8 times 25. Factor out the 8's, and you get 1 over 25. 1,525 divided by 25 is going to equal 61. So 61, factor out the 61s, you get 1 over 25. This last one, a little bit harder to look at. It's 4/10 divided by 10 equals 4 hundredths. Now 4 hundredths equals, if you factor out the 4's, equals 1 over 25. So 4/10 is 1/25 of 10. That's what this is telling you right here. 4/10 is 1/25 of 10. It's a lot smaller, it's a very small part of 10. It's 1/25. So 4/10 is 1/25 of 10. So if you write the equation, 4/10 equals 1/25 times 10, or of 10, you multiply this, you get 4/10 equals 10/25. All I'm doing right now is just playing around with the numbers a little bit and trying to build up your number sense. If you can follow this, if you take some time, work through it, see if you understand each step, you will build up your number sense. So this is 10/25. Well, 4 times 25 is 100. 4 times 10 is 40. So 10/25 is the same as 40 hundredths. Just write it as a decimal, 40 hundredths, and that is equal to 4/10. So 10 times 1/25, 10 times 1/25 equals 4/10. And the last one is somewhat difficult because the constant of proportionality is 2.5, and I would write that as 5/2. And so that's the next page here. And so this is the same as D here. I just wrote it bigger, and I'm going to do a little bit of number sense with these answers here. So the constant of proportionality is B divided by A. So 10 divided by 4 is 10/4. Well, that's equal to 2.5. And what's a way that I can get to that answer 2.5? Well, I'm going to take the 10/4 and I'm going to pull out the 2, which is 8/4. So 8/4 is the same as 2. And what do you have left over? 2/4. Well, that's 2 and 1/2. 2 and 2/4 is equal to 2.5, which is 5/2, and that's equal to 10/4. So that's the connection between 2 and 2/4 and 10/4. Same thing with this one. So now if I have 15/6, how many sixths are equal to 2? Well, 2 times 6 is 12. That's 12/6. What do you have left over? 3/6. So this is 2 and 3/6. 2.5. That's the 5/2. And so the 2 and 3/6 is equal to 15/6. Again, I'm just playing around. I'm just trying to build up your number sense as you follow through with each. And so the way that you do that is you do the same kind of stuff. You play around with the numbers a little bit. So look at this one. I need to pull out 2. Well, how many 20 seconds are equal to 2? Well, that's 2 times 22 is 44. 44 20 seconds is equal to 2. Plus you have 11 20 seconds left over. That's 1/2. 11 out of 22 is 1/2. So 2 and 11 20 seconds, 2.5, that's 5/2. So if I take this and change it to an improper fraction, it's 2 times 22, that's this 44, plus 11, plus this 11 gives you that 55 20 seconds. And the hardest one is this last one here, 7.5 thirds. That's a 2.5. All right, so I have 7.5 thirds. How many thirds does it take to equal 2? Well, that's 6 thirds. 2 times 3 is 6. So that's 6 thirds. What do you have left over? 1.5. Is it true that 1.5 thirds is equal to 1/2? I made a little drawing here. First of all, I'm going to change that 1.5 to 3/2. So 3/2 thirds. I made a little drawing here. This is 1 unit. I divide that 1 unit into 3 equal parts for thirds. And then I divided this first third, actually I divided each of the thirds into halves. So this first third, half of a third is right here. That's 1/2 of 1/3. So that's 1/2 third. And this second one is 2/2 thirds. That's equal to 1/3. And this third section right here, this third part right here is 3/2 thirds. Well, how much of the whole unit is that? Is equal to 1/2. So 3/2 thirds is in fact 1/2. So this is 2 and 1/2. That equals 5/2. Yeah. So if I have 2, a value of 2, how many thirds are 2 whole units? And they are equal to 6 thirds. 2 times 3 is 6. That gives you 6 thirds. Well, that's 6 thirds plus 3/2 thirds. And so both of these are thirds. Now you can just add the numerators together. 6 plus 3/2 is 6 3/2 thirds. And now you change that to an improper fraction. 2 times 6 is 12 plus 3 gives you a total of 15/2, and that's 15/2 thirds. Well, 15/2 thirds is 7.5 thirds, which is where we started, way over here. 7.5 thirds. This is tough stuff. You just have to practice. I got a little bit out of control with this one, but that's okay. You just try to think about the numbers, what's going on, how can you get this 7.5 thirds equal to 2.5 or 5/2? How can you make that make sense? Okay, this is problem number 5. Kieran and May are standing on a corner of a rectangular field. And I actually made the field a square, which is okay. A square is a rectangle. So they're standing right here on this corner, and they're looking across the diagonal to the opposite side along the diagonal. And Kieran says that if the field were twice as long and twice as wide, then the diagonal, this distance from this point here to this point here, would be twice as long. May says that it would be more than twice as far, since the diagonal is even longer than one of the sides. So which one is correct if either of them are correct? Well, if I made the field twice as long, so I doubled the length going this way, and I doubled the width going this way, notice what happens to the diagonal. The diagonal is also twice as long. It's 2 of these squares now. So it's the diagonal of 2 of these squares that are next to each other. So the diagonal is twice as long. So this happens with every length in a scaled image. If you scale an image by a factor of 2, by a factor of 3, by a factor of 4, then every length is going to be scaled up by that same factor. So every side, if it's a scale factor of 2, every side is going to be increased by 2 times. Every perimeter, the perimeter will be increased by 2 times. So in this case, the perimeter is 4 units. 1, 2, 3, 4. If you use a scale factor of 2, now the perimeter is 8. 2 times 4 is 8. So it's 1, 2, 3, 4, 5, 6, 7, 8. And likewise, the diagonal will be doubled, will be twice as long. So it's 1 unit, scale factor of 2, now it's 2 units. So every length is increased by a factor of 2, which is the scale factor. So Kieran is correct.